So this case begins in 1957 in Ubatuba, Brazil, which is near the Atlantic Ocean. And there's a gentleman who's out fishing, and he looks up in the sky and he sees a disc-shaped object moving up at high velocity, and then suddenly the object explodes and millions of pieces of it are thrown all over the ocean, and he's not far from shore. There are pieces on the shore. So he goes back and he collects 3 pieces of this disc-shaped object that supposedly exploded. This was in 1957. He takes those 3 pieces along with a note, and he sends it to a Brazilian newspaper. This gentleman remained anonymous throughout this time period. The only thing we know is based on his writing, he was well educated, but we know nothing else about him. The Brazilian newspaper, I just want to give you a quick feeling of what happens with the samples now. The Brazilian newspaper gives it to a Dr. Fontes in Brazil. Dr. Fontes gives it to an organization in the United States called the APRO, and that happens in 1958, about a year later. APRO then does some work on the sample and then finally gives it to Dr. Peter Sturek at Stanford University. And that's where our testing comes in, because Dr. Peter Sturek knows Dr. Michael Swords very well. He gave Mike some samples. And then Mike and I were talking one day, and I said, hey, I could do some isotope analysis on the trace elements, not just the magnesium. And so that's what kicked all of this off. All right, so now I want you to see this is a sample from 1957 from Ubatuba, Brazil. And I apologize for any light diffraction, but we have a better picture that will show you on the screen now, that which I took with just a low magnification microscope. So you can see that object. Now, while you're looking at that object for a moment, let me tell you a little bit about what we're going to be doing. We're looking at the isotopes of this material because, as I just told you, the history, right, is pretty checkered. We don't know exactly who had it when. We do know, absolutely, that it didn't show up after 1957. It existed then, and it has been tested more than any, quote, UFO fragment that has ever been tested. At least a dozen laboratories have tested pieces. What I'm showing you is a very small piece. It's about 0.05 grams. A lot of it's been lost over the years, but this is from the original sample, and it came from Dr. Peter Sturek. All right, now that you've seen that, we can drop that off the screen. I want to talk a little bit about not the isotopes yet, but what is that sample made out of? Okay, the initial test by Dr. Fontes in 1957 said the sample was 100% magnesium. Well, that's basically true because his equipment at that period of time could not detect any trace elements, so all he could say was, as far as he could determine, it was 100% magnesium. Now, once the sample was shipped to the United States, it was tested by Oak Ridge National Laboratories. Now, you might ask, why would Oak Ridge National Laboratories care about a UFO sample? Well, it was because no one knew how a piece of pure magnesium could show up in Ubatuba, Brazil in 1957. Thus the interest of Oak Ridge National Laboratories. So they tested it using a spectrograph, and they came up with basically 99.9% pure magnesium is what theirs showed. They also found impurities of aluminum, iron, and silicon, and this was in 1958. So now we move to 61. It goes to Dow Chemical, which was one of the top chemistry laboratories in the United States at that period of time. They detected 99.9% pure magnesium, and additionally, strontium, barium, zinc, and copper, which are the same impurities we detect today. So in terms of, the bottom line, what's in this material? It is basically magnesium so pure that in the year 1957, the only places that could have made that magnesium that pure would have been Dow Chemical or some major university laboratories. To give you a feel, 99.88% pure magnesium is comparable to your highest commercial grades today that you can get in a commercial lab. Now, we can make it more pure than that today, but remember, this was found in 57. Okay, so what's the other thing that's of interest here? The strontium. No one had added strontium to magnesium at trace levels other than Dow Chemical. And they had only done that in a laboratory setting. So we're still left with the question of how does magnesium of that purity show up in Ubatuba, Brazil in 1957? All right, so now we move to the next part of the testing, isotope analysis. Okay, the key thing to realize here is that with isotope analysis, you can determine whether something's terrestrial. You can even determine where on the Earth it came from. For example, if there was a dirty bomb and it had uranium in it, a chemist with modern equipment could tell you if it came from the Ural Mountains in Russia, or if it came from, or if it was uranium from southwestern United States, or if it was uranium from the Congo in Africa. That is how accurate high-resolution ICP-MS testing is. Now, the first time this Ubatuba sample was tested in that way was in 1968, and it was tested by what was called the Condon Committee. If you recall, some of you may not be familiar with it, so let me back up a little bit. The Condon Committee was initiated by the University of Colorado in 1968 on request of the United States Air Force. The U.S. Air Force wanted to get out of the business of tests of basically tracking UFOs and reporting on them. It caused them a lot of headaches with Congress, so they were wanting to get out. So here we have the Condon Committee, and they're going to test this Ubatuba sample. Dr. Roy Craig, with a PhD in chemistry, did the analysis. Now, here's the interesting part. Dr. Michael Swartz and I went to Texas A&M, and we got the papers of Dr. Roy Craig, and we looked at this work that he had done. That was among his papers. He indicates there that the magnesium-26 is at, and that's an isotope of magnesium. We have three isotopes, magnesium-24, 25, 26. Well, magnesium-26 is 14%. Okay, so let's stop for a moment. The norm for magnesium-26 is 10.99% up to 11.03. So that's not normal. Yet in the Condon report, Dr. Roy Craig states, and so I'll just quote so that I get his statement right, the Brazil sample did not differ significantly in magnesium-26 isotope content from other magnesium samples. Now, there's two things there that are really outlandish. One, that he would state that 14% is similar to 10.98, 10.99%. The second thing, though, is he left out the 14% number in his report. So I'm mentioning this only because it kind of irritates me that that would be done, and that should not be done. But nonetheless, let's continue through and leave my concern with this and continue with the isotope analysis. So Dr. Peter Sturrock had the sample tested in the 1990s because then ICP-MS became a major tool in chemical analysis. So he had it tested at a lab in Vancouver and Charles Evans, another lab that has places throughout the United States. In the case of the lab in Vancouver, they had slight differences in the magnesium ratio. Charles Evans' lab, it looked fairly good, and we can show it on the screen. It's image number 2, and you'll see on there basically the ratios of using magnesium-24 is your base number because that's your basic element. And so it looks at the ratio of magnesium-25 to 24, versus magnesium 24 to magnesium 26. Now, in the upper left corner, you see all these Dow samples, and you see SUA, which is the Ubatuba sample.
45 minutes.
And if you look on the graph, you see the A, B, C, D, E. You see a circle in the center. That's where the nominal is. And basically, they all fall on the same line. So this is indicating that the magnesium isotopes are terrestrial in nature. Now, can we conclude definitely that's the case? No, because the Vancouver lab did not get that, and the Condon report did not get that information either. Theirs was up around 14. So we don't know right now. So the next step was to do isotope analysis of the samples that Dr. Michael Swords had. And we were going to do one additional thing, right? Today, we could do a lot more than just look at isotopes of magnesium. We could look at the isotopes of the trace metals. That's not something they could do back in the 60s, 70s, 80s. So that was the plan. We identified a chemical lab in Austin. It's the one that I used to manage. They are accredited, ISO accredited. There's basically... they do testing. I'm trying to remember all they test for General Motors, for NASA, for Intel. So their work is considered good work. So Dr. Michael Swords flew down. We met with Dr. Tim Hussein, who manages that lab, and we sat down and discussed how will we test the sample. Okay. Now let's back up for a moment. Remember how that sample was handled. Because of the way it was handled, we really can't do surface analysis because it's been in people's hands. So there's going to be sodium, potassium, calcium on it. So what we decided to do was to etch the surface, to put it in acid, remove much of the surface of it, all of the surface of it, not much. And then we would analyze a small piece of the sample because that's all we need. We didn't have to destroy the entire sample. But the key thing was, in addition to looking at magnesium isotopes, we were going to look at the isotope ratios of strontium, barium, copper, and zinc. So that was the plan. And in 2017, we got back the first results from the lab in Austin, which is called Cerium Lab. They used to be part of Advanced Micro Devices, but they got sold and all sorts of stuff that happens in the semiconductor industry, and so now they're Cerium. So if we look at image number 3, we'll flip that up on the screen. So what you see 3 columns. On your left are the 3 basic ways that magnesium shows up in terrestrial samples. Magnesium 24 being the common source of magnesium, and the 2 isotopes being magnesium 25, 26. The center tells you the nominal abundance. And for magnesium, I can tell you, you could put error bars around that of basically plus or minus 0.04. So it doesn't vary much off of that. To the right is the Ubatuba unknown. So the Austin lab got 79.31. Now that might not seem much to some people, but that is a significant diversion off of what normal magnesium is. The same thing for magnesium 25 and magnesium 26. So we were kind of excited. Oh, wow, got some magnesium. It looks like it's not meeting terrestrial. So then the next thing we did is we looked at the isotopes. Same thing. We got some variations. I won't go into those right now, but we got variations there. So what's the next step? Okay, we need a second lab to verify the first lab, right? Because you can't depend on just data from one lab. You've got to have 2, if not 3 labs that repeat. So that's where Phyllis Buttinger came in, because she identified another commercial lab. Now I'm just going to, for a sidebar, I actually tried to get a university lab first. I talked to Texas Tech, to University of Texas, to Rice University, and University of Houston. All of those universities, once they know the history of how this sample supposedly came to be, they're like verbatim. They don't want to test it. So I could not get a university to test this sample. So we had to go to another commercial lab. So we went to another commercial lab. And if you look, we'll have image number 4 up on the screen. So if you look on image number 4, this shows you basically the results on magnesium isotopes with the new lab, which was in Cleveland, Ohio. And this was by Dr. Arthur Barnes. He was a chemist who worked in the oil industry and had a lot of familiarity with ICP-MS. So if you look where all these samples fell, right? And so if you look on that line you see on the far right, North Atlantic, well, that's basically magnesium samples that came out of the North Atlantic Ocean, and that shows you where its ratio falls. Go way to the left, and you see meteorite, right? Well, that's not because meteorites are 100% magnesium, but that's because some meteorites have a very small amount of magnesium in them, and you can see how they fall way to the left on this. And just to the right of the meteorite is the Ubatuba sample that was tested in Cleveland. And you can see to the right of there the Ubatuba sample that Dr. Peter Sturrock tested. And, various other ones from the Amazon River, this Dow triply sublimed. That was one that was super pure magnesium that Dow Chemical created. That's where it falls in the line, falls very close to the nominal. But you can see way at the bottom is the Ubatuba sample that we originally tested in Austin. So based on what we're seeing here, the isotope ratios of the magnesium in this sample are terrestrial. The problem as to why the Austin lab is so far off, we don't know the answer to. But this is a good example of why it's very important to use more than one lab when you do analysis. You can't just do one lab and stop. All right, so now, even though, that didn't turn out well, we looked at the ratios of the other elements, right? The isotope ratios, because you could have a particular element that might have the same isotope ratio on the moon as it does on Earth, but most of the other elements may not. So it's still worthwhile to look at. If you look at image number 4, that would be image number, let's see, it's the image that has all of the strontium, copper, zinc, and barium on it. And that should be image number 5. Okay, I won't go into this in detail, but if you look at it, you'll see that the various ratios, we've got elements where the ratios don't meet nominal terrestrial abundance. For example, look at the copper, which is the darker horizontal line. In Austin, in that lab, copper 63, copper 65, the first one is higher than nominal. The second one is lower than nominal. And if you look at the Cleveland results, copper 63 looks about right, and copper 65 looks about right. But then jump up to let's go to the zinc values. Zinc 64, which should be 48.6, is 46.99 on the Cleveland sample and 49.41 on the Austin sample. So we've got some major discrepancies between the two labs. So that sent up a red flag. So let's jump now to, okay, so what do we think? Why did this happen? What do we think happened? I think we could say that with magnesium, we know that does definitely appear to be terrestrial isotope ratios. We don't know for certain on the trace metals. And if I were to go back and do it again, here's what I would do different. I would have tried to find first labs that were unique for those elements. In other words, they had experience looking into isotopes for these elements. Although both labs that we used had experience with this high technology equipment and had experience with various isotope ratios, they were not experienced on those particular elements. So I think going back, we would have had them basically isolate the zinc and isolate the barium and isolate the strontium, right? Because you've got a sample here that's like 99% magnesium and very small amounts of trace elements. So we really should have isolated those trace elements separately and then gone and done the high resolution ICP-MS testing. So could we conclude that, this material is extraterrestrial? I really can't say one way or the other. And I hate to say that, but there's still a question on the ratios of the trace elements. My gut feel would be that if we redid them with basically separating each element out by itself, then doing high-res ICP-MS, that they would probably fall in line, but I can't know that for sure. But there's one unanswered part, and that is the magnesium purity. We still don't have a good explanation for why we have 99.88% pure magnesium that shows up in Ubatuba, Brazil in 1957. There's no reasonable explanation for that. That's before satellites existed, so there's no reason that would have been in any way a satellite that he saw. Aircraft do not use pure magnesium, nor do meteorites have pure magnesium. So we're still at a loss to just explain the purity of the magnesium. So that's kind of a summary. Like I said, there's a lot more detail to this that I didn't